Okay, dear students, now we are going to use these formulas that you have seen in the previous chapters, okay, to answer questions found on the textbook, page 322 to page 323. Let's start off with the MCQ options, okay, followed by the structured questions. I'm going to give a very brief overview on how the question should be answered. So down here, I'm actually touching more on the exam skills. The content itself, please read through your notes again or your textbooks again for the actual details. Okay, let's start. Okay, if you look at question 1 of the MCQ, which of the following can be used to calculate the electric power? Now down here, notice they use the word power. So recap, what have you learned? Which are the formulas that can match directly to any of these? Okay, if you recall the 10 formulas that we talked about, power is only mentioned in the last few. So energy is equals to power times time, power is equals to VI, power is equals to I square R, power is equals to V square over R. So these are the few formulas that touches on power. So comparing those over here, okay, the closest one that we can match is power equals to VI, because potential difference is V, current is I. Okay, if you try to match any of the others, it will match a single thing. Okay, so you need to, like I say, read through your own notes to get the knowledge that you need. Okay, so this is just a recall portion at this moment in time. Question 2. A small heater has a rating of 15 volts and 4 amperes. How much energy does it consume if it's turned on for 2 minutes? Now, if you are not very sure what is happening, like what we have tried before, write the symbol above the numbers. It might give a sense of what is happening. So 15 volts is V, because we are talking about potential difference here. 4 amperes is current, I. How much energy? Talking about E. Okay, and time, 2 minutes, T. VIET. Does this remind you of any formula? That's right. We are talking about E equals to VIT. Okay, so if you look at this formula, right, you have to be very careful, because whenever we use formulas, we must be very aware of the units involved. So in this case, 15 volts must be multiplied by 4 amperes of current, must be multiplied by 2 minutes. But 2 minutes here is not the unit that we need to use. Rather, we need to use in the form of seconds. So by changing it into seconds, 2 is multiplied by 60, you get 7,200 joules, and therefore answer is D. Get what we are doing? Okay, so be very familiar with your SI units that is required. Next, number 3. Kilowatt hour is a unit of, if you look at this unit again, kilowatt hour. Which formula uses kilowatt hour? Okay, for those who have forgotten, let's look at this list of formulas again. Kilowatt hours is here. So we are actually referring to energy. So kilowatt hour is a unit of energy. So all this is actually going through in your mind when we attempt all these questions. Okay, question 4. A person uses 3 kilowatts oven for 1 hour and a 2 kilowatt air conditioner for 6 hours. Calculate the total cost of 1 kilowatt hour of electrical energy costs. So if the 1 kilowatt of electrical energy costs 5 cents. So here's the hint already, 1 kilowatt hour. So what formula do we need to use? Okay, so in essence, we are actually using energy again. Okay, but everything must be in kilowatt hours. So for the first one, the oven, 3 kilowatt hours is used for 1 hour. On top of that, the person also uses air conditioner 2 kilowatt hours for 6 hours. So total amount of energy that you have used in terms of kilowatt hours would be 15 kilowatt hours. But the question is asking for the cost of electricity. So when you talk about the cost of electricity being used, I need to take the energy, the total energy that is being used, multiplied by the cost of the electricity per kilowatt hour. Okay, and I'll get, in this case, 75 cents. Okay, be very careful not to change the units of the rate of the electrical use. Okay, because when we change the unit of the rate of electrical use, we tend to make mistakes. So please stick to the unit itself before you do any major changes. Okay, so in this case, if the question gives you in terms of cents, for every kilowatt hour, we stick to using cents every kilowatt hour for the whole calculation until the end before you do the unit conversion if necessary. Okay, like I say, it's if necessary. Okay, question 5. Which of the following is a safety feature that protects the electrical appliances from electrical surges? Electrical surges, okay, for those who don't know, okay, it's just a point in time in the use of electricity when there is a sudden increase in electrical current. Okay, so we are actually talking about sudden increase in current. Okay, so that means we are referring to excessive current. Okay, so if you look at the options given, using a plastic casing with double insulation, this one doesn't give us a protection in terms of sudden increase in current. Connecting an earth wire to metal casing, maybe, okay, but actually it's not either. Connecting a switch to a neutral wire. Now, if you look through this chapter on practical electricity, connecting a switch to a neutral wire is a big no-no, okay, because it infringes on the safety itself. So the only options that is available there in this question would be D, a fuse. In fact, the job of the fuse is to prevent excessive current from flowing into the circuit. So in that aspect, it will have been able to protect the appliance from a sudden increase in current. So answer is D. Question 6. Why is a switch for an electrical device always fitted to the live wire? Now, for those students who have no idea what I'm talking about in this question, okay, you will need to refer back to your textbook and notes and read up. Okay, so the switch we know is always fitted on the live wire. Same for the fuse, it must be on the live wire. Okay, so let's look at the options. Okay, so when we look at the first option, no current flows in the neutral wire. Okay, maybe it's true, right? Okay, for those who have studied up already. So this one might be an option. Let's go through the others and check whether we have any misunderstanding in any way. Okay, B. There will be a short circuit if the switch is on the earth wire. Is this true? Doesn't sound correct. So let's mark it as a cross first. Part C. The device can never be switched on if the switch is on the neutral wire. Is this true? If you think through it very carefully, this is not true either, because the device still is able to be switched on when the switch is on the neutral wire, but unfortunately, it's not safe. So this option is not really correct. Last one, the device can only be isolated if the switch is on the live wire. So this is our option that we need, because this is what the switch actually do. Okay, when you put it on the live wire. Okay, so please read through the chapter on this portion on switches, okay, to find out more. Okay. Okay. Number 7. Okay, what happens when a 2 kilowatt 240 volt electrical heater is connected to a main supply using a plug fitted with a 4 ampere fuse? Okay, if this sounds confusing to you, okay, please go and look at it in detail again. Down here I have power, I have voltage. Okay, but you notice that we are talking about some form of current, right? So which formula talks about power, voltage, and makes use of current? You're right, only P equals to VI. So actually the question is not asking you to calculate I directly, but rather they are trying to ask you to explain why I is affected by the 4 ampere fuse. Okay, so let's find out how much current is actually needed in this case first. Okay, so substituting it correctly, I have 2 kilowatts, which is 2 times 1000 divided by 240. Okay, I will have my current in about 8.33 amperes. Okay, corrected to 3SF. Now you notice that the current required by this electrical heater is actually 8.33 amperes. But if you fit it with a 4 ampere fuse, what will happen? That's right. Okay, the fuse will not work properly. In fact, the fuse would treat it as an excessive current and you function accordingly, okay, which is to melt and break to ensure that this current doesn't flow into the circuit. Okay, so if you look at the options here, okay, A is the answer because when the 8.33 ampere current flows in a 4 ampere fuse, it will melt and break, right? So that melting and breaking is also known as the fuse blowing up. Not blowing up, sorry. The fuse blows. Okay, so the fuse in the plug blows, okay, to protect the appliance, which is your electrical heater, from the excessive current. Okay, so these are the answers for the MCQ. Okay, now we are going to move on to a structured question. We are going to answer them one by one too. Okay, so let's look at these very carefully. In 17.18, okay, figure 17.18 shows the electrical information on the charger of a laptop computer. So there's quite a number of information here, but what is the one that we are concerned about? The potential difference needed to operate, the current needed to operate, okay, and the output, which is how much power can we gain from it. Okay, so you have to read through the details. Sometimes it's not as easy as it seems, okay, but it's not confusing either, so you just have to have some faith in yourself, read through. Okay, so part A, based on information in 17.18, prove that the output current of this charger is 4.74 amperes. They are talking about output current. Okay, so if you want to have an output current, here is I. We need to look at what is the information given for the output option. So if you look at the question here, the output is here, 90 watts. Okay, do you see this? 90 watts. So 90 watts here is actually our power. Okay, I got power, I got current. Okay, think about the formulas that you have. Okay, which one will have power and current involved? Okay, so if you look through, power equals to VI is one of the possibilities. So that means if I can find out what's my potential difference needed, then I may be able to calculate my current. The rest of options will also tell us that if I know the resistance, I might be able to make use of power and the resistance to calculate the current. So these are the options that have ran through in my mind. I would have used 9 or 9 prime as the options. Okay, so let's look at the information again. What other information do I have? Based on this, I do not have anything on the resistance. But I do know that down here, it seems like there is something on the information on the potential difference that is given as an input. So I will suppose that this is my option on potential difference V. Okay, so let's make use of this to calculate. Okay, let's try. Okay, 1A, do not panic if you don't get your answer. Okay, let's try first. Power equals to VI is a formula that I think might work. Okay, based on the question, 90 watts is the power output, but I have an input power of 240 volts, and I need to calculate the current. Okay, so let's calculate from here. I is equals to 90 over 240. Okay, oh, seems like I don't get my answer. Okay, I get my current as 0.375 amperes. Okay, oh my, what is wrong? Oh, I noticed something else. Actually, down here, the output option, there's actually a potential difference too. So I shouldn't have used my 240 volts as a starting. Okay, rather I should have used 19 volts. So this would tell us that this way of doing things might not be correct. So let's try again. Power equals to VI. I noticed that the output potential difference is 19 volts. So 19 equals to 90 watts is equals to 19 volts times I. I calculate my I again. 90 divided by 19. I will be able to get 4.736 amperes, which is around 4.74 amperes in 3SF. There, I've proven that the output current is actually 4.74. Okay, so sometimes it takes a little bit more of reading up in the question to find out the answer. Okay, so like myself, I have read the question insufficiently, and therefore I actually got the wrong answer. Okay, so let's look at part B now. Calculate the amount of electrical energy in kilowatt hour. See, calculate the amount of electrical energy in kilowatt hour consumed in 1 month, which is 30 days. If the laptop is connected to a charger for 6 hours a day. Wow, there's so much information. But if you look at the information for time, it's actually broken up into quite a fair bit. Okay, so let's calculate the time required first, okay, to help us in the calculation. Okay, the question says that this laptop is operating on a 1 month basis, which is 30 days. Each day, it operates on a 6-hour basis. Okay, and the question actually wants us to calculate in terms of kilowatt hours, so my unit here has to be in terms of hours, and I'll keep it that way. I do not need to calculate in terms of seconds. Okay, so if I've done it correctly, I should get 180 hours. Okay, but I have not thought about the power. Okay, based on this question, the output power is 90 watts. Okay, but I cannot just take 90 and multiply by 180 here, because the question wants us to calculate in terms of kilowatts. So 90 watts, in order to change to kilowatts, I need to divide by 1000. So I get 0.090 kilowatts. Okay, so after doing that, it's not the end. My question wants me to calculate energy. Okay, and I have to do so. So 0.090 multiplied by 180. Okay, 0.09 multiplied by 180. Use your calculator, please. Don't use your mental calculation. Okay, you get 16.2 kilowatt hours for the use of a laptop that operates on a 30 days, 6 hours per day cycle. Okay, so this is the answer that we need. Any other queries, please read through again and clarify with me directly. Okay, now we move on to question 2. Okay, question 2. Oh, it talks about the 3-pin plug. Okay, we went through this lesson before. Okay, so looking at this, you need to recall very quickly what is actually happening. Okay, so look through. What is P? What is Q? What is R? What is S? Okay, don't panic. Just answer accordingly. Okay, so if you have recalled very fast, S is actually the fuse. R is our live wire, which should be brown in color. In this case, because I use a photocopied version of the textbook page itself, so you won't be able to see the color, but I think you are able to see the color in your book. Okay, earth wire, which is green and yellow for the wire P. Okay, and Q should be our neutral wire. Okay, neutral wire is blue. Okay, and you see this thing over here, this squarish thing that is on top of the wire itself. Okay, this actually serves a purpose. Go and find out what is it. Okay, it's important. Okay, so name the options P, Q, R, and S. Oh, I've actually named all my options already. Okay, now state the function of S. So what's the function of the fuse? Just state it out. Okay, so for question 2A, okay, I've already labeled my question itself on the question paper. I'll just copy over now. P, Q, R, S. P is my earth wire. Okay, I'll add in the other information here, green and yellow. Okay, it's a green and yellow wire. Q is our neutral wire. Okay, it's supposed to be in blue. R is our live wire. It's supposed to be in brown. And S is our fuse. Okay, fuse is a device that prevents excessive current from flowing into the circuit. Okay, so what's the function of the fuse? Okay, it is a device that prevents excessive current from flowing into the circuit. By melting and breaking when the current exceeds the given rating. Sorry, rating spells as R-A-T-I-N-G. Okay, so please go and read up the chapter itself, why I give my answer in this way. Okay, to find out more. Okay, question 3. In figure 17.20, okay, which is this figure, okay, the live, neutral wire and earth wire are labeled as N, E, and L. Okay, live is L, neutral is N, earth wire is E. complete a diagram below to show how the wires should be connected to the two power sockets. So these are two power sockets, right? Yeah. So these actually have to talk about the ring, okay, circuits. Okay, so we have to be very careful because the power sockets doesn't just directly connect to the main supply. It has to connect by via a ring circuit. Okay, you need to read through that particular portion in the chapter. Okay, unfortunately that time we didn't have time to go in very much detail about it. Okay, so I shall demonstrate how to do here. Basically, within the room, all the earth wires will be connected together, okay, through the ring circuit, and then all the live wire will be connected together by another ring circuit. Neutral wire will also be connected together by another ring circuit. Okay, so live wire is always the right hand side of the socket itself. Earth wire is always the top of the socket itself. Neutral is always the left hand side of the socket itself. So how am I going to connect everything together properly? Okay, so this is what we are going to do. First, I'm going to create my live wire, okay, around the circuit. Okay, so now the box is a little bit tight for me, so I'm going to use the outside of the box. I'm going to draw outside the box. Okay, so let's say this is my live wire, circuit ring. Okay, and it will be connected to the live wire itself. Okay, so after it goes around the room, whenever I have a socket that needs the live wire, I'll just connect to this ring itself only. Okay, so in a way, it's actually creating parallel circuits on its own. Okay, so this is a live wire. Earth wire, same thing. Okay, yep. Okay, I'm going to create an outside ring here to make it more clear for all of us. Okay, I purposely draw across the outside but not connecting to the live wire itself because it is a ring on its own. So this earth wire will be connected to the earth pin. Okay, and down here as well, earth wire connected to the earth pin. Okay, the big dots, big black dots will tell us where the connection is. Okay, so make a guess, how am I going to draw for the neutral wire? Yeah, same thing. Okay, same thing, I'm going to create another ring around it. Okay, but because it's a little bit tight now, so I'm going to just go and do it inside. Okay, I'll just use this innermost, okay, to create this ring first. Okay, so this last ring in the innermost here is actually our neutral wire, and my neutral wire will connect to the neutral terminals. Okay, my neutral wire will connect to the neutral terminal there. Okay, so this is what we call the ring circuits. Okay, you need to read up on that chapter itself. Okay, part B. Okay, the position where the 10 ampere mains fuse should be fitted. So recall again, where should the fuse be fitted? That's right, it should be fitted on the live wire. Okay, so find out where's your live wire again and put the fuse there. Okay, so I shall express it over here, 3B. Okay, to blow up a little bit. Okay, this is the live wire given. Just now I've drawn a ring circuit. Okay, I've created a ring circuit. Okay, for the wires to be connected, right? Okay, so where should the fuse be drawn? Okay, the fuse should be here. Okay, so this is the symbol for the fuse. Okay, it looks like a resistor, but the line actually goes through the box itself. Okay, so the 10 ampere fuse has to be here. so that when excessive current flows in the circuit, these fuse will blow and prevent excessive current from flowing into the circuit. Okay, so that's question 3. Okay, let's move on to question 4. Sorry, let's move on to the next question, which is the free response questions. Okay, usually for the O levels, okay, they will look at all the options here. When you look at all the options here, the O levels will actually be something along these lines. Okay, and you need to try to read through, okay, especially the paper 2 options. Okay, so let's look at the questions here. I hope that you have actually practiced on it. Okay, so let's move on. Okay, down here, this figure shows a lighting circuit. Okay, each light bulb has some form of power and the potential difference required to operate. Okay, and the number of bulbs in the circuit is variable. That means I can increase or decrease the number of bulbs accordingly. Okay, part A, the arrangement of the light bulbs are in a particular one and the advantage of this arrangement. So if you look at this arrangement carefully, right, what is this type of arrangement? That's right. Okay, so actually this arrangement is a parallel circuit. So what's the advantage of this arrangement? Very good. Okay, the advantage of this arrangement is when one of the light bulb blows, okay, the other still can work. So that's actually what they want you to write down. Okay, so just write down when one of the light bulb blows or not working, the other light bulbs will continue to operate. Okay, so this is one of the main advantages of a parallel circuit. Okay, and this is why all our lighting circuits are arranged in a parallel option. Okay, parallel circuit. Okay, next one, calculate the combined resistance of the 3 light bulbs as shown. Take note, it's 3 light bulbs here, but you notice that the question doesn't give you the resistance for you to calculate straight away, but you do notice that there is information on power and V, potential difference. Okay, so how are we going to calculate the resistance from here? Okay, so taking notes of your formulas. Okay, you are given power, you are given the potential difference. Okay, so power, potential difference, I can calculate I. But this formula can't give me resistance. Look through the rest. Power, potential difference, and the resistance here. So this is the formula I need to use. Okay, so really look through. If you can't remember how to calculate, how to get this formula, it's okay. All you need to do is just calculate the current, and from the current, use this V equals to IR again with the potential difference again. You should be able to get the same resistance. Okay, so let's use that. Part B. Okay, power equals to V squared over R. I'm trying to calculate my resistance here. So resistance equals to V squared over P. Substitute accordingly. 230 squared divided by the power 80 watts. Okay, and I will be able to get my resistance. Okay, but you notice that my resistance will not be exact. Okay, I'll get 661 ohms. Yeah, I'll get 661 ohms. Did I do everything correctly? V squared over R. V squared 230 squared. Yeah. Okay, you notice that I get 661 ohms here. Okay, 0.25 to be exact. Okay, but I will not use the exact value here. In fact, I'll use the rounded off value. Okay. Okay, what's the reason for this? Because we know that in real life it's not exactly 661.25, and there's a high chance that we are using the rounded off value all the way actually. Okay, so using this idea, I want to calculate the total resistance will be 1 over 661 plus 1 over 661 plus 1 over 661. Okay, and calculate the total resistance. Okay, but this is only the starts. Okay, you get 3 over 661, right? Okay, but do remember down here, this formula, we are only talking about the inverse of the resistance. Okay, we have not actually calculated the resistance itself. Okay, so if you do it correctly, you get 220 ohms corrected to 3SF again. Okay, so 220 ohms. Okay, if I'm not wrong. Okay, yeah, so yeah, just try your best to answer the questions. Okay, if anything is wrong, never mind, just carry on. Okay, so because we will have this idea called error carry forward, so any mistake they commit early on, okay, it should be accounted for at the end. Okay, and we'll just make use of the wrong answer all the way, because you also won't know what is happening in the actual exam itself, right? So next one, state the purpose of the fuse and what happens to the fuse when the switch is on. So if you look at the current requirement, okay, of this circuit itself, okay, you won't know anything very fast. Okay, but you can actually calculate it out later. Okay, but what's the purpose of the fuse? Okay, the purpose of the fuse is, yes, like what we have mentioned earlier. Okay, the purpose of fuse is actually the answer in the question 2B of section B. Yeah, so I'm not going to copy this again. Okay, so let's do the second part of this option. Okay, state what happens to the fuse when the switch is on. So basically you need to find out how much current actually flows first. Okay, so based on these circuits and the total current, total resistance here, okay, we are able to say that we are going to use this formula, V equals to IR. Okay, 230 is the potential difference given by this question. Okay, and I need to calculate the currents required to operate this circuit. Okay, and the total resistance is 220. Okay, and okay, if you do it correctly, you should be able to get I is equals to 1.045 amperes, which will round off to 1.05 amperes to 3SF. So does this exceed the fuse in this question? No, this doesn't exceed the fuse in this question. So what do you think will happen to the fuse when you switch on? Nothing happens. So that's your answer. Okay? So you need to read the question very carefully. Can? Okay, part D. Table 17.2 shows the daily energy usage for the circuit, suggests what may have happened to the circuit on days 3, 5, and 6. Note that the circuit is only switched on for an hour each day. Okay, so down here, they talk about the daily energy usage. Okay, for the circuit. Okay, so suggest what may have happened on days 3, 5, and 6. So let's look at 3, 5, and 6. 3, 5, and 6. Okay, so what do you think happened? Okay, notice that on day 3, the energy usage is actually lower. On day 5, the energy usage is 0, even though it's supposed to be switched on. Okay, And on day 6, the energy usage is higher. Yeah? So just give some answer that you think might answer these questions. Okay, so on day 3, when the daily usage is lower, what do you think happened? Okay, day 5, what do you think is happening? Day 6, what do you think is happening? I'm not going to give you an answer here. Okay, I want you to try. Okay, just come up with some answer that you think is logical and then propose it. Okay, because in the actual exam, there's no standard answer for this one. There are multiple possibilities here. Okay, so just give it a go. Okay, and next one, question 2. Okay, question 2. In figure 17.22 shows part of the electrical circuit of the kitchen where the main supply is 230 volts and the lamps in the circuit are identical and each is rated at 50 watts and 230 volts. The rice cooker is rated at 2 kilowatts and 230 volts. Okay, so there's a lot of information here. Do not be worried. Okay, so you just need to read through again and try to figure out. So down here, they're given you a circuit diagram. 230 volts is the potential difference across the live wire and neutral wire. Okay, and this rice cooker, okay, rice cooker is going to operate at 2 kilowatts and at 230 volts. Okay, but each lamp, okay, each lamp here is going to operate at 50 watts and 230 volts. So you notice that the circuits are open here. So that means I can control the number of lamps that I want to use as well. Okay, first one, part A, calculate the current flowing through each lamp. Okay, so down here they're actually asking for the operating current. Okay, so let's calculate that one. 2A, okay, let's have it over here. Okay, part 1. Okay, they are giving you that the power, they have given you power is 50 watts each for each lamp. Potential difference needed by each lamp is 230 volts. Okay, so they are asking you to calculate current. So the only formula we are using is P equals to VI. Okay, so okay, substitute your things accordingly. I should be equals to P over V. So I get 50 divided by 230. Okay, so the current required by each light bulb is 0.21739 amperes. 0.217 amperes is in 3SF. Okay, so I'm presenting my answers in 3SF here. Okay. Okay, next one, fuse X. Okay, so down here you notice that part 2 they ask you to calculate the current flowing through fuse X, but you notice that fuse X is being governed by the switches A, B, and C. Okay, so you need to make a judgment call, okay, whether they are talking about 1, 2, or all 3 switches will be on. Okay, so I'll say that I'm assuming all 3 switches will be on and I'm going to operate from there. Okay, so since this one is a parallel circuit, okay, and I know that one switch, okay, is connected to each lamp. Okay, so that means if I have one branch having 0.217 amperes flowing through it and 3 branches here would mean that I need to take this same value multiplied by 3, okay, because of Kirchhoff's law. So part 2, okay, total, in fact maximum, okay, current that we can flow, okay, would be the answer from part 1, which is 0.217 multiplied by 3. So this is a maximum possible current that I can have. Okay. Okay, so 0.651 amperes in 3SF. Okay, so this is the maximum possible current that I can have. Okay, for that fuse X. Okay, so part 3. Okay, the heating elements. They're asking you to calculate the current needed for the heating element in the rice cooker. We know that the power and potential difference is given by this. Okay, so let's calculate from there. Power equals to VI already. Again, okay, so current is P over V. Okay, so 2 kilowatts means 2000 watts divided by 230 volts. Okay, so 2000 divided by 230, I'll get 200 over 23, which is 8.69565 amperes. Correct to 3SF, 8.70 ampere, 3SF. Okay, so this is the current needed for the rice cooker. Okay, so part B. Okay, let's look at what the question wants. One of the fuses in the circuit is fitted wrongly. Identify the fuse and indicate on the figure the correct position of the fuse. Okay, so if you look at the circuit diagram given, okay, and think through where should the fuse be connected, you realize that actually all the fuse has to be on the live wire. Okay, so X is on the live wire, Y is on the live wire, but Z is not. So actually Z should not be here. Z is most likely required over here. So this has to be the position of Z. Okay, because Z has, in a way, this Z has to control the current flowing into the whole circuit itself. That's why it should be positioned even before fuse X. Okay, so I've answered part 1 already. Part 2. In addition to using fuses, electrical appliances like rice cookers should be earthed. On figure 17.22, draw an earth connection to the rice cooker. Okay, so now you ask yourself, earth connection, where should the earth connection be connected to in the rice cooker? Okay, for those who have recorded your theory very well, okay, the earth connection must be connected to the metal casing of the rice cooker. So from your rice cooker metal casing, okay, over here, okay, draw a earth connection. There. This is what we should see. Okay, where the earth wire is connected to the metal casing of the rice cooker. Okay, so I've answered part 1 and part 2 already. Okay, part 3, what's the purpose of the earthing the rice cooker? So what's the purpose? Explain everything. Okay, so when you talk about earthing of the rice cooker, there are a few things that we need to mention. Okay, I'm going to just point out the few important things that we need to see. Okay, so first thing that we need to talk about is in event of fault. Okay, in this case, we are talking about the live wire touching the metal casing. Okay, so your answer should have this as one of the sentences. Okay, the meaning of this in one of the sentences. Second, okay, talk about how the earth wire works. Okay, so what does the earth wire do? Okay, so in this case, when the live wire touches the metal casing, it actually conducts away the current from the metal casing to the earth wire. Okay, and last part, I need to talk about the preventing of electric shock. By user. Okay, so I should see these 3 points inside your answers. Okay. Okay, so now part C. Okay, I'm not going to write down everything. You need to go and do it yourself. Okay, part C. What do you think the ratings of fuse X and fuse Y should be? Okay, remember the fuse cannot be the same value as what you require for operating the circuit. It has to be slightly larger to what you need. So looking at the options given, looking at the position of the fuse X, you notice that the fuse X have to accommodate a maximum of 3 light bulbs operating at the same time. Okay, so fuse X should be able to accommodate 0.651 amperes easily. Okay, so based on what we have as the fuse rating itself, okay, fuse X needs to be probably 1 ampere. Okay, 1.0 ampere. Okay, it cannot be too far off. I cannot choose a 13 ampere fuse here because it's going to be very dangerous. Okay, fuse Y is just on the live wire leading to the rice cooker, so I need to know how much current the rice cooker actually need. Okay, based on previous calculation, rice cooker is 8.70 amperes. You need 8.70 amperes. Okay, so based on our options of the needs of the current itself, okay, the fuse Y needs to be, okay, if I remember correctly, okay, there's a 10 ampere option. Okay, so I have to choose something that is slightly higher, okay, than what we need, okay, but yet within the recommended fuse rating itself, okay, slightly higher. Okay, so if 10 amperes is not the, if there's no such thing as 10 ampere, then probably it will be a 13 ampere. Okay, please check. Okay, I can't remember exactly now. Okay. Part D. Okay, the rice cooker is switched on for 15 minutes per day. Okay, calculate the number of kilowatt hour consumed by the rice cooker in 1 week. So same as just now in the section B, more of the question, you need to calculate the amount, right? So time is down here 1 week. 1 week is 7 days. Okay, multiplied by number of hours used in 1 week is 15 minutes, so 15 over 60 of an hour. So total number of hours used in a week is 1.75 hours. Okay, but you want to calculate the energy involved. Power given is 2 kilowatts. Okay, so energy would be equals to power times time. Okay, so 2 kilowatt multiplied by 1.75 hours. Okay, so your final answer should be 3.5 kilowatt hours. Okay, last one, part 2. Given that 1 kilowatt hour costs 28 cents in Singapore, calculate the cost of using the rice cooker for 1 week. Okay, so they are actually asking you to calculate the cost. Okay, so given your answer in part D is this. Okay, part D part 1 is this. Part D part 2 would mean that the cost of electricity is actually taking 3.5 kilowatt hours multiplied by the 28 cents in dollars. Okay, so just leave it in dollars. Remember, we try to avoid changing the units too much because we tend to make mistakes. So if you have done it correctly, you should get 98 cents. There, this is the answer. Okay. Yeah, so any clarification needed, please check with me directly. Okay, so let's look at the last question. Okay, question 3. Given that the main supply is 240 volt, calculate the current that flows through the electric fan when you switch on. Okay, so in this question, they tell you that the power is 500 watts for the fan, power rating. Okay, and it has a metal casing. Okay, and now I tell you that the main supply is 240 volts. Okay, so you have power, you have V. They ask you to calculate the current. What formula are we using now? Okay, that's right. Okay, so the formula that we need to use is P equals to VI again. So you notice that it's actually quite repetitive, okay, in the form of what we are doing. Okay, so substitute accordingly. 500 equals to 240 multiply by I. Calculate what's the I. It should be somewhere around half. Okay, 2.08333 amperes. Leave it to 3 SF. Okay, I have 2.08 amperes. Okay, part B. Okay, the manufacturer of the fan is given the information in this table by a wire supplier. Based on data in the table, which type of wire should the manufacturer buy and why? Okay, so if you look at the current needed is 2.08 amperes here, right? Okay, and look at what is given. Okay, you notice that most of the wires, or in fact one of the wires is out of the picture already. Okay, so A is out of the picture. Why? Because the maximum current that you can carry is 1.8. But if you look at the current needed by the fan is just 2.08 amperes. So B to E are still possible options. Okay, so based on that, you give your own conclusion on which wire you should be using. Okay, or which wire should the manufacturer be using, and explain why. Okay, for me, I will just choose one possibility is choosing wire B. Okay, what's the reason? Okay, is able to accommodate the wire needed, the current needed by the fan. Okay, that's one consideration that I have. Second consideration I have is the wire is not too thick. Okay, so think about it. In reality, do we really want a wire that is very thick, or do we want as thin of a wire as possible? Okay, so those are considerations that you might want to think of when you are answering such questions. But of course, it's not limited to that. You are given your choice. Okay, so there are actually multiple answers here. Okay, part C, based on information given about the electric fan, would you recommend that the manufacturer uses a 2-pin plug or a 3-pin plug for the electric fan? Why? Okay, so there are some considerations to take note. Okay, when you use a 2-pin plug, it does not have an earth wire. When you use a 3-pin plug, there is an earth wire. Okay, but if you look at the question itself, it has a metal casing. So make your own judgment call now. Do you think you need a 2-pin plug or 3-pin plug? Okay, actually the answer that is required here is a 3-pin plug. Okay, why? Okay, so here's the first consideration. Okay, please write in sentence form. Down here, I'm just only writing in point form. Okay, first concern is there is a metal casing. Okay, so when there's a metal casing and when there's faults, the current will flow into the metal casing itself. Okay, second concern, okay, is that the current, okay, but the current that you calculate is 2.08 amperes. It's actually quite high. Okay, so the current needed is actually sufficient to cause hurt. Okay, so that's why I will recommend a 3-pin plug. Okay, that's the answer. Okay, so there are some other considerations that you can think of out there. Think of logical ones and put it in. Okay, there's no one final answer for this. Okay, so hopefully this video helps you in the answering of these questions, and I hope you have gained sufficient practice from this exercise itself. Okay, thank you very much.